Here is the first section on hydraulics. What can you do with hydraulics? Well, you can run the primary flight controls like rudders, elevators, and ailerons on transport category jets, big biz jets, big turboprops. You can also power the secondary flight controls like flaps, trims, slats, slots, speed brakes, spoilers. You can run the landing gear, even in a Seminole. We use hydraulic systems to power the landing gear system. Wheel brakes, even in a 172, we use a hydraulic system, or actually one for each side, to power and control the wheel brakes. And there are some transport category jets, big biz jets, that use hydraulic power to operate the thrust reversers. Pascal's law essentially has three parts to it. Let's see if I can draw this very well. Okay, there we go. Now, if we have a confined system, we'll say that this is a container. And we'll put a PSI gauge all over this thing. Or put PSI gauges all over this thing. Pascal's law essentially says three things. First of all, Pascal's law says that the force applied to the side of the container is at a 90-degree angle to the side of the container. Here we can draw it like that. Draw it in that way. Pascal's law also says that the pressure anywhere in the system is equal to everywhere else in the system. So all of these pounds per square inch gauges, all these PSI gauges, are going to read the same thing. He also figured out if you could drill a little hole in here and pump some more fluid in here, and the pressure here would go up. The pressure would go up the same amount everywhere else. So let's see how much of that I got right. Okay, pressure is at a 90-degree angle. PSI is the same. And if you bump up the pressure anywhere, it'll cause the pressure to go up everywhere. Okay, it's as if I had taught this before. Force equals area times pressure. Let's use an example right here. We'll take a really small cylinder, and we're going to say that this one is round, and that there's a piston in here. We'll have put a rubber O-ring around it so it can slide up and down and not have any fluid leak out. And we'll have a big diameter piston over on this side. And again, we'll put a rubber O-ring all the way around it. Force equals area times pressure. Let's just say that the area of this cylinder, remember if we were looking down on it, it would be a circle. If we were looking down on this thing, it would be a big circle. We'll pretend that that's a circular circle, not an oval. We'll say that this area right here, the area equals 1 square inch. And we'll say that the area here equals 10 square inches. And let's say that they would put a big fat rock pushing down on here. And let's say at the same time we push down right here with a force of 10 pounds. Force equals area times pressure. If we push down here with a force of 10 pounds and this rock weighed just the right amount to keep this piston here from moving, what would be the pressure inside of here? And just for fun, we'll change it to red because 5606 general aviation hydraulic fluid is red. They dye it red. So the force on this side right here is 10 pounds equals the area, which is 1 pound, times pressure. So we can solve for pressure. Divide by 1, divide by 1. We get 10 equals pressure. And we're doing everything in pounds per square inch. So 10 psi is in here. So if we had a psi gauge, this would read 10. Now Pascal's law says that in this confined system here, that the pressure is the same everywhere. So guess what the pressure is in here? 10 psi. So on this side we can go force equals area times pressure. We can calculate how much force does this rock have to have on this piston. The area of the piston is 10 square inches. The pressure is 10 psi. Wow. Force equals 100 pounds of force. So this rock here has to weigh 100 pounds for gravity to pull it down enough to equate to, or to equal, or equalize rather, the 10 pounds of force on this other side. You'll notice that there is a direct and linear relationship between the force needed, or the force used, versus the area of the piston, or the area of the cylinder. Here we have a small force and a small square inch area. Here we have a large force and a large area. So there's a direct relationship between the force and the area. Why? Because the pressure is going to be the same. So essentially the ratio of these two are always going to stay pretty constant. Hey, volume equals area times distance. Hey, let's go back. Volume equals area times distance. Hey, it's all there. Yay. Let's see if I can figure this part out here. Get rid of some of this stuff. Oh, wait, I'm not going to worry about getting rid of that. Volume equals area times distance. Oops, distance. Volume equals area times distance. Okay, let's just say for fun that we push this piston down 10 inches. So the volume that we have displaced is equal to the area of the cylinder, which in this case this is 1 square inch, equals 1 times the distance. We moved it down 10 inches. So 10, so we have volume equals 10 cubic inches. Well, this fluid had to go somewhere, and we'll get to it here shortly, but the fluid is not going to be compressed. In a hydraulic system, we're going to use an incompressible fluid, so this volume of fluid had to go somewhere, and sure enough, it's going to go over here. So it's going to push this piston up. We can figure out how far. Volume displaced equals the area times the distance. So in this case, we know what the volume is. We know the volume is 10 cubic inches. 10 cubic inches equals the area of this piston, which is 10 square inches. 10 square inches times the distance. So now we can solve for distance. Divide by 10 on each side, and we get 1 equals distance. So this piston is only going to go up 1 inch. You'll notice now that there is an inverse relationship between the area versus the distance. The volume, again, is going to stay constant, where on this side any volume that gets displaced has to go to the other side. So the ratio of the area and the distance is what we're going to be concerned about. So if we're thinking about if we're thinking about distance traveled, then if area is small, distance is going to be big. If area is small, distance is going to be big. If area is large, then distance traveled is going to be small. Okay, mechanical advantage. Let's take a teeter-totter. Everybody's played on a teeter-totter. We'll put somebody on this side. We'll say that they weigh 50 kilograms. Then we'll put somebody on this side, and we'll say that they weigh 150 kilograms. We'll say that the total distance right here is 6 meters. So that means that each side of the fulcrum, or each side of the pivot point, or each side of the teeter-totter has 3 meters to it. Now, we can balance this teeter-totter by either adding more weight on this side, or we can do it by scooting this person in. So if we scooted this person in, we'd have 1 meter times 150 kilograms would equal 150 kilogram meters. Over here we have 3 meters times 50 kilograms equals 150 kilogram meters. So they're going to balance out. Wow, a weight times a distance. Sounds kind of like a moment in aircraft weight and balance calculations. So you'll notice here that in this example here, we can either use a small force over a large distance, or we can use a large force over a short distance to get the same force applied at this fulcrum or at this pivot point. So the same thing goes with the piston in a hydraulic system, is that in that hydraulic system where we have a small area versus a large area, we can push down here. In the previous example we had 10 pounds, and here we could apply 100 pounds because the ratio was 1 square inch of area, and here it was 10 square inches of area. So there, that direct relationship still keeps working for us. Now, however, the problem is if we want this to move a large distance, then this side is going to have to move a huge distance. So there is a downside. Although it takes less force, we have to push it a large distance. A smaller force is going to have to cover a larger distance. Here we have this much greater force, but it's only going to move a little tiny bit, a small distance. So that's okay. What we're going to end up having to do, however, is this piston right here, we're going to have to move it a long distance to get anything to happen. So what we're going to do in an airplane or a helicopter is this part right here. This is going to be the pump, and this part right here, that's going to be the actuator. So we're going to have to move this pump a bunch, back and forth and back and forth and back and forth, quite a bit, just to get this actuator to move a little bit. So that's the downside. The positive side is we get a big force. We can have a really large force. So there's the mechanical advantage of hydraulic systems. Now on the test, I'm going to ask you the difference, or I'm going to ask you a list and say, list all the characteristics of hydraulic systems, list all the characteristics of hydraulic fluids. So first we'll go over the systems. They're pretty lightweight. If you look at transport category jets that have been in production for 40 or 50 years, 60 years, you'll find that if the pilots can't provide enough power with their hands and arms and feet to operate the flight controls, hydraulics has been the system of choice to power the flight controls. And the reason is because it has a lot of force out of the actuator, but it doesn't weigh too much. If you change the fluid and change the filters at the recommended intervals, hydraulic systems are very accurate or very reliable. They go for a long time without failing. Getting the power from the pump to the actuator, it's not 100% efficient, but it's pretty close. So it works out really well that whatever power you generate, it's going to get to the actuator. And of course, in a hydraulic system, the fluid has to be incompressible. Just for fun, I'm going to keep drawing this diagram. At least it's fun for me anyway. So we have the pump on this side, and we have the actuator on this side. When we push this piston down, it's going to displace a volume. But let's say we had an air bubble in here. What might happen is we might have 10 cubic inches of fluid move out of here, but this bubble might get compressed and get smaller, and this area, this volume right here, might have been 7 cubic inches, and therefore only 3 cubic inches of fluid would have been displaced, and the piston would not have gone as far as we needed it to. That's because air is compressible, and we need things that are not compressible. That is, when we apply very high pressure to it, it does not change its volume. And in this case, with hydraulic fluid, for practical purposes, it doesn't change its volume. As far as pilots are concerned, it's an insignificant amount. So we need the fluid inside of our system. We need this hydraulic fluid to be made out of stuff that doesn't compress, that does not change its volume even when a very, very high pressure is applied to it. You'll notice that that's the first item on the list of characteristics of all hydraulic fluids, is that it's incompressible, that it cannot be squished. You cannot make it a smaller volume even when you apply high pressure to it. You need medium viscosity. A high viscosity means it's thick, means that it doesn't flow very easily, and that's good for lubrication. So we want it thick enough to lubricate, but we want it thin enough or have a low enough viscosity that it'll travel through the hydraulic fluid lines easily without causing too much friction. So medium viscosity is a compromise. It's a high enough viscosity to lubricate, but it's a low enough viscosity to not cause too much heat and not take too much power just to push the fluid around. We also need a high viscosity index. Viscosity index is talking about how much does the viscosity change with a corresponding change in temperature. A lot of liquids, when you heat them up, they get thinner or get a lower viscosity, and when you cool them down, they get thicker or get a higher viscosity. If that changes its viscosity a lot with just a small change in temperature, that's a low viscosity index, and that is bad. What we want is a high viscosity index. That means you can change the temperature a lot and its viscosity doesn't change very much. I'll give you an example. Let's say you have 2 cups of water and 2 cups of pancake syrup. You put a cup of water and a cup of pancake syrup in the fridge and cool it down to a little bit above freezing, and you put the other cup of water and the other cup of syrup in the microwave and heat it up just below the boiling point of water. So you've got a water and syrup at 2 or 3 degrees Celsius, and you've got a cup of water and a cup of syrup at, say, 95 degrees Celsius. If you take the cold cup of water and the hot cup of water and pour them out simultaneously, they'll pour out at about the same rate. They have the same flow, so they have the same viscosity. I've poured hot water and cold water, and I haven't noticed the viscosity changing. So you could say water from 2 degrees Celsius to 98 degrees Celsius has a high viscosity index because in that temperature range, its viscosity pretty much doesn't change at all. The syrup, on the other hand, if we cooled it down to 2 or 3 degrees above Celsius, it almost wouldn't even pour out of the cup. And if we had heated it up to 95 or 98 degrees Celsius, it would have poured very, very easily, even especially compared to room temperature. So in that case, the syrup from 2 degrees Celsius to 98 degrees Celsius has a very low viscosity index because its viscosity changes so much, even though we've only changed its temperature by about 90 degrees Celsius. So in that case, the log cabin syrup has a low viscosity index. You also need it to not foam. If the hydraulic pump pulls in a bubble of air because the reservoir is full of foam, then that air is compressible and it won't displace fluid. So we need a fluid that when it gets pumped back to the reservoir, the bubbles all break right away. So beer, unless it was flat, would be a terrible hydraulic fluid because of all the carbon dioxide bubbles in it. We also need high thermal stability. Thermal stability talks about how well the characteristics of the hydraulic fluid will remain the same even though you've heated it up for a long, long time. So high thermal stability means that you can heat it up and keep it at high temperatures for a long time, and it tends not to break down into other chemicals and then have terrible qualities like not lubricate very much or not flow very easily or foam a lot or have a viscosity change. This is one reason why you change car engine oil and airplane piston-powered engine oil, is because after a long enough time, say 3,000 miles worth, its thermal stability starts going down and you need to change the oil because it's not doing what it's supposed to anymore. Well, that's the same for hydraulic fluids. So the higher the thermal stability, the better it is. Now, the most common type of hydraulic fluid that you're going to find out, say, at Prescott Airport is MIL-H-5606. Now, technically, that O is a 0. It's really 5606 or 5606, but people have been calling it 5606 for decades, so don't sound silly to your airplane mechanics. It's 5606. Now, it's designed around a military specification, number 5606, and if you want to build something, say, for instance, jet fuel or jet engine oil, or in this case, hydraulic fluid, you have to comply with this particular military specification. It's very similar to a TSO, a technical standard order, in that if you build it or manufacture it to this certain tolerance, to this certain quality, then you can sell it to the military. And the FAA approves this military specification 5606 for a hydraulic fluid. Now they dye it red. It's made out of petroleum products, but they dye it red so you can see it. It's a little on the flammable side. It's not like gasoline. It's more like engine oil. How easily can you catch engine oil on fire? Well, if you put the heat to it and hold it there for a little bit, it'll catch it on fire and it'll sustain a flame. Now, if you've got a really high pressure system, say 3,000 psi, and there's a pinhole leak, just the size of a pinhole, hence the name a pinhole leak. There we go. Then it'll spray out in a mist, and it's a lot easier to evaporate, and that's really what you need to catch something on fire, is to get it to evaporate. So if it was misting, it would burn pretty good. Couple of good things about 5606 is it's not bad for paint. If you spill it on the paint, you don't have to worry about cleaning it off right away. It won't peel it off. And you can leave it on your skin quite a bit as a human being, and for most people, it doesn't bother the skin unless you're soaking your hand in it like 8 hours a day, every single day of the week. So if you get it on you, it's not that big of a deal. It's like getting car engine oil on your hand or airplane engine oil. You wipe it off, but it's not like you got to go wash it off with soap and water right away. Skydrol, on the other hand, is a synthetic oil, synthetic hydraulic fluid. There's a couple of different kinds. There's purple and green. You'll want to read the Pilot Operating Handbook, the Approved Flight Manual, to see what kind of Skydrol to put into your airplane. The FAA likes it because it doesn't burn very easily. You can pour Skydrol out and try to light it with a match, and if you hold a match or a lighter close enough to it, you can get it to start to burn a little bit. But when you pull the ignition source away, the flame will go out. So we're going to say that Skydrol is relatively non-flammable. It does not burn very easily at all, which is in contrast to 5606. And of course, if you're in a little airplane like a 172 and you got 2, 3, 4, 5 quarts, 2 or 3 quarts of 5606 in the brakes, and you crash, you're a lot more worried about the 100 octane catching on fire and bothering you than you are 1 or 2 quarts of 5606. But if you're in a transport category jet, a big biz jet, a big turboprop, now it's not just 1 or 2 quarts of hydraulic fluid. It's going to be gallons and gallons and gallons of it. And the FAA decided, with these big old honking planes, if there's a crash, we'd like to have you put a hydraulic fluid in it that doesn't burn very easily. So that's why the FAA likes Skydrol. The airlines like it because it weighs less per quart. It has a lower density. It still is incompressible, but it doesn't weigh as much as 5606 does. And when you're talking, let's just say, I'm making this up, let's just say it weighs 2 pounds a gallon less, and you got 300 gallons, well, that's 600 pounds. 600 pounds of fuel savings divided by 2.2 pounds per kilo, that's about 180 kilos. Well, that's a lot of cargo that you could put on the airplane every single time you flew. That's a couple of people or quite a bit of baggage or mail or extra fuel you could carry. So it lowers the empty weight of the airplane so you can carry more cargo, passengers, or fuel. The downside of Skydrol is that it tends to eat paint. If you get Skydrol on the airplane paint, you need to wash it off right away. And I don't mean just wipe it off, but you got to wash it off with soap and water. Same thing about humans. If you get Skydrol on your skin, you need to wash it off with soap and water. If you get it in your eyes, you need to flush it out with water immediately and go see a doctor immediately. This is the downside of operating an airplane with Skydrol. So if you're going to go out and do a walk around on your transport category jet, don't touch the hydraulic stuff unless you're prepared to walk away and go find a sink with soap and water and get it off of you right away. Otherwise, because it'll feel like a bad sunburn after a little while. So you don't want to take off and a half an hour into the flight, your hands feel like they've been sunburned, and if you happen to wipe your eyes or stick your finger in your ear, then that's going to hurt too, and it could actually swell your eyes shut, and that doesn't work out very well when you're flying to have your eyes swelled shut. Okay, basic hydraulic system. You essentially need a pump, fluid lines, and an actuator. You've already seen that diagram. We had a pump, we had the actuator, and you need at least one fluid line to get the fluid to and from the pump versus the actuator. And in order to have hydraulic power, the two things you need are a volume of fluid, and you need it at a pressure. You need a displacement of volume so that the cylinder or the actuator will actually move, but it's not going to move unless you have a force, and that force is dependent upon the pressure. So you got to have a pressure of fluid, and you got to have a volume of fluid before an actuator is going to move and push anything and actually have hydraulic power. Okay, as we go along with these hydraulic components, you're going to need to know for the test what's the purpose, and then what's the function, and then if you're given a schematic of it, you're going to need to be able to identify which one is which. So here's a pump. I'll show you a picture of it here in a second. Dun, dun, dun. There's a picture of a pump. Hydraulic fluid. Let's change colors here. Hydraulic fluid comes in and it gets filled in these cavities. This gear rotates around in this direction. This gear rotates around in this direction. So the fluid in here, it gets squished out and pushed over as these teeth move in. This fluid moves over. So this right here is the pump, and the reservoir would be on this side. This would be to the actuator. You don't have to draw this on the test, but I will show you a diagram. So this is a pump. I'll go back. Oops. And what's the reason? The purpose is, why is it on the airplane or helicopter? Why on aircraft? Why is it there? And this function is, how does it do its job? So the function is the how, and the purpose is the why. So why is it on board the aircraft? So we can have a lot of hydraulic power. How does it do it? It's an energy conversion device. We're going to have tons of energy conversion devices in this class. It's going to take the kinetic energy or the rotating energy off of the engine, and it's going to turn it into hydraulic power, which means we're going to have a volume, and it's going to be supplied at a pressure. Actuators. Actuators, I'll come back to those here in a second. Here is a double acting actuator. We can pump fluid in this direct side, and if the pressure is high enough, force equals area times pressure. The area of this cylinder, if we looked at it from the side, the cylinder is round. The area of the cylinder times the pressure is going to equal the force. So it's going to tend to push this piston in this direction, and whatever's hooked on here, it's going to move. This black dot right here and right there, that's really a rubber O-ring that goes all the way around to keep the fluid from leaking past. And the fluid on this side is going to be all full of fluid, and it's going to be pushed out back to the pump or back to the reservoir. So if we supply fluid on this side, the piston gets pushed in this direction. If we somehow switch that and we pump the fluid in this direction, there's going to be an area up there. Area times the pressure is going to equal the force. It's going to push the piston back in the opposite direction, and the fluid over here is going to be redirected back to the reservoir or back to the pump. So there's a double acting actuator. What is the purpose of it? It's there on the airplane. That is, what's the why is it on the aircraft? It's there to move stuff. It's there and the function, which is the how, and it's there to convert hydraulic power, and of course that's volume and pressure. It's there to convert hydraulic power back into kinetic energy. So you could say that it's doing the exact opposite of what the pump is. It's just changing it from the power that was used to get it out to the actuator and changing it back into some type of a kinetic energy. Fluid lines are there. What's the why? Why are they there on the aircraft? To allow transfer of hydraulic power. And then of course the how. Does it do it? By making sure the hydraulic fluid doesn't leak. It contains hydraulic fluid while it's moving. That one's pretty tough. There's three basic types of hydraulic systems. We're going to cover the first two in this chapter. There's the one-line system, the electro-hydraulic, and then the system that has dedicated pressure and dedicated return lines. First we're going to do the one-line. Here is a one-line general aviation brake system. The master cylinder is the pump. We're only going to need one fluid line. It allows the fluid to go from the pump to the actuator and from the actuator back to the pump. And then of course we have to have the actuator. This one happens to be single acting, so you ought to have this diagram here. Here's the pump. We'll go ahead and label these first. and I'd rather call it a pump than a master cylinder. This is a fluid line. Here is the actuator, and this is the brake disc, and it can be spelled D-I-S-K or D-I-S-C, and these are the brake pads. That's the part you're checking for when you're looking at the brake pads on a 172 or a Seminole to see if they're thick enough and be airworthy. You're looking at this distance right there to see if the brake pad is worn down. So you notice we got a pump. Looks like I forgot to fill in the O-ring right here. You're going to push down with your feet. You're going to push down with your feet, and we're going to have a volume of displacement. And so this fluid is going to go out to the actuator, and it's going to push the pads together, and it's going to squeeze it against this disc, and there's a lot of friction in here. And so we're going to convert rotating energy of the wheel and the inertia of the aircraft into heat. Now, what isn't shown in here is that there's a spring in here that's pushing the piston up. You probably notice that when you let your foot up, the pedal goes up. It's because there's a spring in there. So when the spring goes up, it pulls some fluid in, so some of this fluid inside the actuator gets pulled back. And this space in here can be really, really small. So as long as they're not touching, this space can be really small. So there doesn't have to be the volume displaced is very low in a general aviation brake system, because all you really need is force. Of course, the diameter here, let's just say for fun that the area equals 0.1 square inches, and we'll say that this actuator right here is 3 square inches. Well, the ratio of force from here to here is a ratio of 0.1 to 3. 3 over 0.1 equals 30 over 1. So if we push down with 10 pounds of force, remember there's a direct relationship between area and force. So if we push down with 10 pounds of force and the ratio is 30 to 1, then that means we can have 300 pounds of force pushing the actuator and pushing the brake pads together. So it's a force multiplier. We have this mechanical advantage, and we're going to use this one fluid line to allow fluid to go to the actuator, and we're going to allow that same fluid line to allow fluid to go back to the pump. Now on a Cessna, on top of here, underneath the pedal, there's a big reservoir to keep the fluid in. In other airplanes, they have a separate line with a reservoir. And we'll talk more about reservoirs on another slide. Here is the electro-hydraulic system. You're going to find electro-hydraulic landing gear systems. You'll receive airplane landing gear systems. And when I say smaller, I'm talking about less than 12,000 pounds. It's not an exact number. And what powers the hydraulic motor instead of your foot is, what powers the hydraulic pump instead of your foot or being manually powered, it's powered by an electric motor that can go in 2 different directions, so it's reversible. And the pump, therefore, is driven electrically. And we're going to have fluid lines that allow fluid to go to and from between the pump and actuator, and we're going to have double acting actuators, and I should have a picture here. Ta-da! Now this is a portion of, I deleted a bunch of stuff, I erased it. This is a portion of the electro-hydraulic landing gear system found in a PA-44. So here is our reversible electric motor, a circle with a capital M in it. That's the electrical symbol for a motor. And of course here you can see the fact that we have a hydraulic pump. It's driven by electricity. And let's just say, I might as well draw them here. Here's our actuators. They're double acting. We can pump fluid in one direction and push the actuator in one direction. We can pump fluid in the opposite side and have the actuator move in the opposite direction. So they're double acting. And then of course we have fluid lines that allow fluid to go to either side of the actuator and to and from the hydraulic pump. So just for fun, I'm going to show you what happens. Let's just say the motor spins the pump in this direction and fluid goes in this direction. So it fills this up, and it makes fluid go to this side of the actuator, and it moves it in that direction. Fluid is also going to go, personally I don't like Piper's diagram, but pushes that one up. And it also goes in this direction. Not coloring within the lines. And of course it's going to push the actuator in this direction. So maybe we'd call this the up direction. So in that case you can see this fluid line and this fluid line and this fluid line are the pressure side. And at the same time, we'll use blue. At the same time, I know it's dyed red, this blue fluid comes in this direction. It goes up here. The fluid in this side of this double-acting actuator goes up here. And the fluid on this side of the double-acting actuator, it goes here. So all we're doing is pumping the fluid around in a big giant circle. And then, of course, if we reverse it,